Hello everyone, this is Group 92 and we are here to give the final presentation for our project which is ChestGAN, Auxiliary Classified GAN-based data augmentation for improved chest cancer type detection. So what is the problem and why it needs to be solved? So we want to improve chest cancer type detection and create an automatic tool for it. So because the manual cancer detection is tedious and it's prone to human error because of the diversity and in the cancerous lesions which occurs because of the different types of cancers, patient type, and also the stage. And also, while addressing this, we want to improve the performance of the models by addressing the limited availability of the data, and in turn, reduce increase recall and reduce false negatives. So we take a data set from CAGO, which includes three types of chest cancers, which is adenocarcinoma, large cell carcinoma, squamous cell carcinoma, and the normal chest CT scans. So before running the models, we process the data. So as we can see here, we have substantial imbalance in the number of channels. So we only include images which have the four channels, which is RGBA, and we also resize the images to 300 by 400, which were chosen because of the mode of the distribution with respect to the width and the height. So the inputs would be the chest CT scan images and the data augmentation techniques, which is AC-CAN. The output would be synthetic images, which are generated through AC-CAN, as well as labels from the classifier, which would be CNN, and finally the visualization of the model performance.
So this is our proposed network architecture. So here we are trying to enhance the training data by adding the synthetic images with the AC-GAN architecture. So the AC-GAN architecture has two heads in its discriminator. One is the class head, which is telling how good the model performs in classifying different images into accurate labels, and the source ahead is basically saying what is the model's performance to discriminate between fake and real so that the generated images are good. So here we are first of all giving the training images to the AC-GAN, then AC-GAN will generate the synthetic images, and then we will enhance the training data set to feed into the CNN model and finally do the classification. So here we can see the baseline of our CNN classification model. So we can see that there are two convolutional layers followed by three linear fully connected layers. And then we can see that we have also done some hyperparameter tuning here and reported the best hyperparameters for number of epochs, batch size, what is the loss function, what is the optimizer that was used, and so on. This is the performance of our baseline model without the data augmentation with AC-GAN. So since we were mainly focusing on the recall, you can see that the recall values across all the classes as well as the macro recall and the weighted recall all are doing bad in performance. So this is the performance of our AC-GAN model of generating the synthetic image. So you can see the performance of the two heads. The first one is the class accuracy that is like increasing with time. So that means the model is at the end doing good in terms of classifying the images into the correct levels. And the source loss is telling us what is the model's performance in discriminating real versus fake images. So if the source loss is too high, that means the discriminator is not performing well in discriminating real and fake. And if it's too low, that means the generated images are not that good. So we want something in between. So we can see that the model's performance is converging at somewhere between 0.4 to 6, which is good for our model.
So we used Optuna for hyperparameter optimization. Some of the parameters that we used are NGF for generator channel distribution, NDF is for distributor channel, and lambda class is used to balance the weights between the generator and the distributor. We did some regularization in this process, and here are the hyperparameter values that we used. So from the summary result, we can see that from the data distribution table, we can see that the augmented data set distribution performed really well. So we added some synthetic images to create two different models. One was the unbalanced model with augmented data set, and the other was the balanced model with the augmented data set. We can see that the weighted recall improved from improved like 9% with the unbalanced augmented dataset from the baseline model. There was, however, a slight decrease in the weighted recall with balanced dataset compared to the unbalanced dataset, but it was still higher than the baseline. The large cell class performance remains challenging, however, although the recall improves like 20% from the baseline to the balanced dataset, but it is still lower than the others. Overall, the recall metrics in this indicate that the effectiveness of the GAN-based data augmentation was very successful. All of our team members have some prior experience working with the ML data framework. So here are the references that we use for the project. Thank you, everyone. That's all for our presentation today.